Have you ever wondered why the most advanced brain-computer interfaces still feel like they belong in a lab rather on your wrist or in your headphones? For decades, the biggest hurdle hasn't been the technology itself, but the tedious requirement that every single user needs their own custom calibration session. It's as if every time you bought a new pair of glasses, you had to visit an optometrist to have them tuned specifically for your eyes before you could see anything. But what if we told you that science has finally cracked the code to make these interfaces work universally, right out of the box? Today, we are diving into a groundbreaking shift in how we connect our minds to machines. We'll explore why deep learning is finally ready to understand our brains without needing endless adjustments, and how new contactless methods are turning sci-fi concepts into everyday realities. You'll discover why this matters for everything from helping patients with severe motor impairments to creating seamless virtual reality experiences. Stay until the end because the convergence of these ideas suggests a future where talking to computers with our thoughts becomes as natural as speaking with our voice. For years, the field of brain-computer interfaces has operated under a limiting assumption that every human brain is too unique to be understood by a general model. This meant that researchers and clinicians had to spend hours performing subject-specific calibrations for every new user or even every new session. Imagine trying to learn a new language, but having to relearn the alphabet every time you spoke a sentence. This bottleneck slowed down progress, restricted access to only those who could afford the time and resources for calibration, and prevented the technology from scaling to the general population. The problem wasn't just the complexity of the brain, it was the belief that we couldn't find common patterns across different people. We were treating individual variability as noise that had to be filtered out manually, rather as a feature that could be learned. This approach kept brain-computer interfaces trapped in specialized laboratories, unable to reach the millions of people who could benefit from them, such those with ALS or other conditions that limit their ability to communicate or move. But now, a wave of new research is changing the narrative. Scientists have discovered that by leveraging larger, deeper deep learning architectures, we can actually achieve what was once thought impossible: domain generalization. Instead of tuning a model to a specific person, these advanced AI systems can analyze data from hundreds of subjects to extract universal neural signatures. Think of it like teaching a child to recognize a face. Initially, they might need to memorize the specific features of their mother. But with enough exposure to many different faces, they develop a general concept of what a face looks like, allowing them to recognize strangers instantly. Similarly, these new deep learning models have learned to identify the P300 response and other key brain signals that appear across all humans, regardless of their individual quirks. Furthermore, this isn't just about better software, it's about a revolution in hardware interaction too. New studies have validated contactless paradigms, such using airborne ultrasound or head position stimulation, to evoke robust brain responses without needing electrodes glued to the scalp. Researchers have successfully generated somatosensory responses by stimulating specific points on the palm or even the back of the neck, proving that we don't need invasive or cumbersome setups to read the mind. One particularly exciting finding shows that headphone-based delivery can yield stable brain responses comparable to complex multi-speaker systems. This means the bulky equipment of the past is being replaced by the devices we already own. By combining these deeper AI models with non-invasive hardware, we are moving toward a zero calibration framework. The data suggests that when we stop trying to force every user to fit a narrow mold and instead let the AI learn the breadth of human diversity, the system becomes not only more accurate but also more robust. It turns out that the variability between subjects isn't a bug, it's the very data needed to train a truly universal interface. So, what does this mean for us, for AI, and for the future of humanity? The implications are profound. First, this democratizes access to brain-computer technology. By removing the bottleneck of per-session calibration, we can deploy these systems rapidly in critical situations, from emergency response units to consumer electronics. Imagine a world where your headphones can detect your focus levels in real time, or where a patient with locked-in syndrome can communicate their thoughts instantly without a technician spending hours setting up equipment. This shift accelerates the timeline for clinical adoption, making life-changing technology accessible to populations that need it most. Moreover, this convergence of computer vision, deep learning, and neuroscience signals a new era of human-computer symbiosis. We are moving away from fragmented, static tools toward dynamic, fluid interactions where machines understand our intentions as naturally as another human would. This paves the way for immersive virtual reality and robotics that can respond to our touch and our thoughts simultaneously, blurring the line between the digital and the biological. While questions remain about the optimal balance between model depth and data quality, the direction is clear. We are building a bridge to a future where the interface between mind and machine is seamless, intuitive, and universally available. As we stand on the brink of this new era, it's exciting to realize that the barriers we once thought were insurmountable are simply challenges waiting to be solved with the right perspective. The Transitio.